Thank you, Andre. Thanks, Patrick, for this invitation, for the introduction. And yes, I'm going to be talking about event-triggered control for partial differential equations, in particular reaction diffusion PDEs. And I would like to say that event-triggered control for PDEs is a topic I've been working on for the past 8 years, more or less. I initially focused on event-triggered control for linear hyperbolic PDEs. Then I moved to parabolic PDEs like reaction diffusion PDEs. And now I'm interested in event-triggered control for more complex dynamics, let's say coupled parabolic PDEs with hyperbolic PDEs, possibly with non-local terms. But before that, I think that the first step is to towards studying more complex dynamics is to consider the problem of event-triggered control for reaction diffusion PDEs with input delay, because as we will see, the delay can be represented as a first-order linear hyperbolic equation. But let me start simple. Let me spend some minutes to try to motivate the study of event-triggered control in a PDE context. Okay, so this is one of my favorite examples. So consider the problem of control of a network of open channels of navigation. Open channels can be modeled using the so-called Saint-Venant equations. And we want to regulate, say, the flow and the level of the water. And the flow rate is controlled through actuators, hydraulic actuators like mobile spillways or sluice gates or water gates, right, that are placed at the boundaries. So this problem can be reformulated as a boundary control problem, for which we can find in the literature a lot of contributions, a lot of results concerning the design of continuous time boundary controllers. But the question now is how to perform a realistic actuation on the system, and also how to implement the continuous time controllers. And I ask that because in real life, we cannot move, we cannot open and close the water gates continuously. It has to be done either periodically or aperiodically, or when some event calls for it, okay? So if we think about implementation into a digital platform, when we think about sample data and zero-order Holt implementations, but we should be asking how often we should update the control value in a periodic fashion. What is the period? How small we should take the period? And in general, for PDEs, it's been quite challenging to provide constructive ways to select the period in sample data schemes. And it is here that event-triggered control can play a crucial role, because we can act on the system on events and only when needed, and it is done efficiently because of that. And in real, this is particularly beneficial in large-scale application like this one, especially if we consider cascade open channels, a network of cascade open channels with hydraulic actuators which have inertia. So I think that event-triggered control can play a crucial role here. So the key message is to act and to update the control value only when needed. Let me discuss another interesting application for which event-triggered control can play a crucial role. It is about the problem of traffic congestion control. Okay, there are several strategies for traffic management. And I would like to point out run metering strategies and varying speed limit control strategies. So in run metering, the inflow is controlled through traffic lights, whereas in varying speed limit, the traffic flow is controlled through displaying the advisory speed that drivers have to adapt to, right? And for both run metering and varying speed limits, we can reformulate this problem also as a boundary control problem. Boundary control problem with a PDE of hyperbolic type. In this case, the ARZ model. And we can find several contributions for the design of continuous time boundary controllers. You want to explore those control strategies using, for example, run metering of varying speed limits. I recommend consulting the recent book by Yu and Miroslav Kristich, and you will find several strategies, continuous time controllers designed by the backstepping method. But the question now is, okay, how to implement those controllers into a digital platform? And either if we use run metering or varying speed limits, the modulation cannot be done continuously. For example, in varying speed limit, we cannot. It is not feasible to display continuously the advisory speed. It has to be done periodically or aperiodically, or better, on events based on a predefined policy while verifying the state of the freeway. Okay, so again, event-triggered control can be beneficial here. And what about parabolic PDEs? Well, they find also applications in different fields, for example, tubular chemical reactors, in large-scale networks, multi-agent systems in the context of deployment, information control, applications to epidemics, among many others. And all these applications motivate not only the modeling and control by a PDE setting, but also event-trigger control. In particular, I find that epidemics is quite relevant, and it underlines not only the benefits of using event-triggered control in managing epidemics, but also the need to consider and to handle delays in the process. I'm not expert on epidemics, or I want to discuss the very well-established models for epidemics. But let's suppose that we can enrich a model of epidemics by considering a propagation phenomena. In this case, we talk about hyperbolic PDEs, or when accounting for spreading or diffusion phenomena, we are talking about parabolic PDEs. So at the end, suppose that we may propose a model, a mixed model between parabolic and hyperbolic PDEs that are also subject to input and output delays. So to understand how the delays are involved in the process, just recall the recent COVID-19 pandemic. So during the pandemic, we used to do tests, right? COVID test to determine whether we had COVID or not, right? But before the rapid COVID test, the results took quite too much time to arrive. So we can view this problem as a sensor delay problem. Okay. On the top of that, if we think about mitigation policies, let's say isolation, lockdowns, vaccination, those mitigation policies are essentially control actions, right? But the real effect of those mitigation policies is not immediate. It takes some time. It takes some time to really observe the impact of the mitigation policies. So there we are talking about actuator delay. So we see that there is a clear need to compensate for the delays, to account for the delays, and this really motivates the application of a PDE setting and delay compensation. So I really think that there are a lot of opportunities, not only in for delay compensation and for distributed parameter system, but even triggered control for distributed parameter system. So whatever the infinite dimensional system you want to deal with, let's say parabolic, hyperbolic, couplings, time delay systems, even trigger can really play a crucial role. But be aware that it brings a lot of challenges, depending on the nature of the distributed parameter system. Challenges also related, theoretical challenges related to, for example, the avoidance of the Zeno phenomenon, and in turn related to the well-posedness of the closed loop system. And let me say also that for the analysis and design, we can use different methods, backstepping method for PDEs, Lyapunov techniques, modal decomposition, semi-group theory, ISS for PDEs, pretty much the whole machinery we've been developing for control and estimation of distributed parameter system. And it's worth mentioning that most of the ideas and strategies developed for distributed parameters, for even triggered control of distributed parameter systems, draw inspiration from what has been done finite dimensional systems. I mean, for linear and nonlinear ODEs. We can find several contributions, relevant contributions, which include different strategies, static triggering conditions, dynamic triggering conditions, or strategies that rely on a small gain approach. Okay, so as I said, these works have been very useful to extend, in particular, to PDEs. And you can find already several contributions, for example, even triggered in domain control for reaction diffusion PDEs, the works by Anton Selivanov and Emilio Friedman. You can have a look at even triggered for linear hyperbolic systems using Lyapunov techniques and dissipativity conditions at the boundary, even triggered control based on modal decomposition, observer-based design, LMI-based even triggering condition, even extensions to already to nonlinear PDEs, and also to other classes of PDEs like the Schrödinger equations. On the top of that, we can find applications other than traffic, for example, to load moving cables, to the Stefan problem, which include moving boundaries, and even applications to neuroscience. Okay, so I really think that there are a lot of opportunities in this field. Okay, having said that, this is the outline of my presentation. I will first talk about event triggered control for reaction diffusion PDEs without delay first. So I will start with sample data implementations, the preliminaries on sample data, and some issues that motivate to move forward to event trigger control. And we are going to talk about backstepping design and emulation of the backstepping. And then we are going to consider the case with delay. Now, at the end, I will share with you some short-term perspectives, ideas, and a couple of open problems to take away. Okay, so this is the reaction diffusion PDE with constant parameters that we want to deal with. So reaction diffusion PDE with Dirichlet boundary actuation. Lambda is the reaction parameter, which is large enough. So in open loop, the system is unstable. And this boundary controller was designed using the backstepping method for PDEs, which includes a Volterra transformation whose kernel, in this case, can be given explicitly and in terms of a modified Bessel function. This function, this kernel includes the parameters of the plant and a parameter C, which can be chosen a priori, and it's very helpful to boost the convergence, to adjust the decay rate of the closed loop system. But the question now is how to implement this controller in a digital platform. How we should, how we update this boundary control. So the first attempt is to use a sample data scheme, right? We talk about emulation of the that boundary controller in the sense that we know already the controller, right? And it is updated periodically in a sample and hold fashion. Okay, so we keep constant the control value on uniform intervals of time, and we update the controller at tj plus capital T, some period T, right? That needs to be found carefully. And in this work, Iason Karafilis and Miroslav Kristich managed to provide a constructive way to select the period. However, this approach turns out to be very conservative, so the periods are very small, and it's not feasible for implementation, not even in simulation. Now, so I think that the conservatism is a feature that we encounter typically in periodic schemes. If the period is very small, it means that we need to update the control value very often, and it implies overuse of computational and communication resources. And it is here again that even triggered control may offer an efficient way of using resources, because we update the control value only when it's needed, while guaranteeing the theoretical properties of the closed-loop system. And in my view, it represents a more realistic approach for the actuation of the PDE system, as I've been emphasizing during my talk. So by building in the same setting, we want now an even trigger boundary control scheme. So now the control is updated on events. So we keep constant the control value and this interval of time, okay? And we TJ, we call it the triggering times, and we update the control value according to an event trigger mechanism, which verifies a condition, a state-dependent condition, which says when the control value needs to be updated. And we built on the backstepping approach. So for those who are not familiar with the backstepping, let me recall that with the backstepping approach, we want to transform the closed loop system, unstable system, into a stable system that we call a target system, a system easier to deal with. In this case, we want to transform the original system, the reaction diffusion PDE, with a piecewise constant signal at the boundary. Okay, use script D, and we use this backstepping transformation, the direct backstepping transformation, and the inverse. In this case, they admit a closed form solution. Okay, so after transformation, I notice that there is a term here, V, what we call deviation of actuation, which is actually an input holding error. So this deviation appears here at the boundary, and it can be considered as a perturbation, as a disturbance, and we want to assess the robustness of the system with respect to that disturbance. So we look for ISS property with respect to D. So this target system with Dirichlet boundary condition and a perturbation at the boundary is ISS with respect to D. It has been proved that it is ISS, but let me recall that so far as I know, it hasn't been possible to confirm or to prove that this class of system is ISS if we considered a Lyapunov analysis, and the main obstruction is the lack of an ISS Lyapunov function. a coercive Lyapunov function, I would say. Well, anyway, the good news is that we can find an ISS property, but using other tools like a modal decomposition, Fourier series, and Parseval theorem. And this is the L2 norm, the ISS estimate in L2 norm that was obtained by Iason and Miroslav. And what is interesting here is that this asymptotic gain gamma can be characterized explicitly in terms of the parameters of Lie. Okay, so keep in mind this gain. And now we define formally the event-triggered control strategy, which includes, the definition includes the feedback, okay, which is updated on events, and the triggering condition, which monitors the deviation of actuation and compare it with the L2 norm of the state and the L2 norm of the state the last time we have sampled. And beta here is a design parameter for the sampling speed. Okay, so it may happen that this set can be empty. So in this case, we don't trigger anymore. We say that we form already a finite set of triggering times. In the case this set is not empty and this condition is satisfied, we say an event is generated, we update the control value, and we reset D to 0 again. But in that case, the natural question is, can we avoid the Zeno phenomenon? And the answer is affirmative. We can avoid the Zeno phenomenon, and let me show you some ingredients on how to prove that there is no Zeno phenomenon. So for that, we consider the Sturm-Liouville operator, A, linked to our reaction diffusion PDE, and we need in particular the eigenfunctions of the operator A. Okay. Next, we recall the deviation of actuation, which is given here. And typically, in order to prove that there is no Zeno phenomenon, we need to study how this error behaves, because we don't want it to experience finite time escape. So we studied this, and for that we take the time derivative on an open interval and try to find upper bounds. Okay, but we can rapidly notice that when taking the time derivative, there is a term here that cannot be upper bounded. And this term is very, very problematic. So what we try to do is to use some approximations. So we start with a Fourier approximation of the kernel gain. We call it G, okay? And then we try to approximate the deviation D through what we define as tilde D. Tilde D here is still a deviation, but with a nicer kernel. Okay, so now we take the time derivative, and then we are able to find useful upper bounds. I won't enter the full details, but we can find some upper bounds, and then we try to estimate D tilde in terms of the intersampling times, and we use the triggering condition. So we end up with this inequality in terms of the intersampling times, where all parameters here are positive, and this allows us to conclude that there exists a positive lower bound between two triggering times. And this lower bound will depend on the parameters of the system, will depend also on the parameter of the triggering condition, and it doesn't depend on the initial conditions of the system. So we say that it is uniform. Regarding the stability, we built on the target system, what I call perturbed target system. Okay, so we know now that this target system is ISS with respect to D, and we use the triggering condition because it guarantees that this inequality holds. So we want to try to keep the error when sampling small enough, right? We use also a fade in memory estimate and some other computations, and we enforce this inequality that we replace here. And then we use the bounded invertibility of the backstepping transformation to relate the result of the target system to the original one, okay? And we end up with this, this estimate where phi here is an expression which depends on the parameter of the triggering condition, the asymptotic gain, and the control gain. Okay, so we want this condition to be less than 1, this is the small gain condition. And again, we use the bounded invertibility of the backstepping transformation to relate back the result to the original system. So at the end, we obtain the global exponential stability of the closed loop system. Okay, and now we consider the case of reaction diffusion PDEs with input delay, which is actually the core of this talk. This is a very recent joint work with Miroslav Krstić and Florent Kudohode. The paper is still under review. I will make the preprint available in HAL, which is the French archive. I want to say that Florent is a former PhD student of the University of Paul Sabatier in Toulouse. He worked in the last laboratory in Toulouse under the supervision of Lucie Boudouin and Sophie Tarbouriège. And now Florent is a postdoc in the Technical University of Crete, working under the supervision of Nicolas Beccaris Liberis. Okay, so we studied the same class of system, but now notice that there is a delay in the input, a known constant input delay. Having a delay in the input changes quite a lot of things, and it brings more challenges. And delay compensation for this class of system was solved by Miroslav in 2009 using the backstepping approach. One of the key ideas is to represent the delay as a first-order linear transport equation, which is a linear hyperbolic equation with a transport speed 1 over d. So here we have the PD representation where x is the spatial domain belonging to 0, 1, and the control action takes place at the boundary of the transport PDE at x equal 1. So the idea is to transform this PDE unstable PDE system into a target system, which is can be proved to be exponentially stable. And if we look at the transport PDE here, you can notice a 0 at the boundary. And this transport PDE has a very interesting property feature that I like very much. This transport PDE is fixed time stable. So this 0 propagates through the spatial domain, and then it reaches the left boundary. So after delay, the transport PDE vanishes. So we end up, after delay, we end up with a simpler heat equation, which is by nature exponentially stable. These are the backstepping transformations. Notice that they clearly include the delay, and the kernels can also be obtained explicitly. So if the delay is 0, we can come back to the kernel for the delay-free case, okay? And similarly, these are the kernels of the inverse transformation. And we are, in particular, we are going to build on these kernels. We'll see in a few minutes. And we want to see how the event trigger control scheme look like for this problem. And we can apply the same ideas, I mean, to represent the delay as a transport PDE. And now we have a piecewise constant signal at the boundary. And after transformation, using the same backstepping transformations, we have now the deviation of actuation at the boundary of the transport hyperbolic equation. Okay, so this transport PD is no longer fixed time stable. Okay, this piecewise continuous signal, the deviation of actuation signal propagates through the domain, and then it reaches here. So we need to study carefully this target system. Let me say that, okay, this is the boundary controller, the event trigger boundary controller. In terms of the kernels of the direct transformation and the states of the original system, but we can also represent the controller in terms of the kernels of the inverse transformation and the states of the target system. And this formulation, we use this formulation, it's particularly convenient for some technical considerations that I will discuss a little bit later on. We define formally the event trigger control strategy. Okay, once again, we have the boundary controller that we want to update on events according to a triggering condition. So we monitor the deviation and we compare it with now the max of the L2 norm of the parabolic state and the supremum norm of the hyperbolic state. Okay. And once again, we ask ourselves, can we avoid the Zeno phenomenon? And the answer is yes. We study again the deviation. We trying to find the time derivative and try to find some useful upper bounds. And here there are several terms that depends on the boundary conditions and depend on the kernels of the inverse transformation. So fortunately, we can get rid of some bothering terms. And one of the advantages of working with the kernels of the inverse transformation and the states of the target system is precisely because we can get rid of some terms that that cannot be upper bound. So at the end, we try to find upper bounds and then integrate on this interval, and we end up with an estimate in terms of the t minus tj. And here there is a function gamma, which contains also other parameters. A0 is A1 and A2. All of them can be characterized in terms of the parameters of the system and in terms of the kernels of the inverse transformation that we know are explicit. So we can characterize this in some cases explicitly and in others numerically. Okay, and now we assume that an event is triggered at tj plus 1. Okay, so we use triggering condition and we obtain an inequality in terms of the intersampling times that allows to conclude that there exists a lower bound between two triggering times. A lower bound, which we call dual time, and depends on the parameters on parameters of the system. Somehow depends on the delay and depends also on the parameter of the triggering condition. And here we have the full picture of the closed loop system. And this is the main theorem. This is the main result we want to prove. And I want to point out this inequality in this condition. It is a delay-dependent condition. It involves the delay and it involves the parameter of the triggering condition. So we want to choose beta small enough such that this condition holds. Okay. So for the stability analysis, we rely on the target system. We call that we have here the perturbation that propagates, but before it reaches the left boundary, this term here can be also considered as a perturbation for the boundary perturbation for the parabolic part. Okay, so we look for ISS property for the DAB omega system, right, with respect to ZT0, and we look for the ISS property for the transport PDE with respect to DT. And we rely on these estimates that were obtained by Iason and Nicolas. And then we use a fading memory estimate. We write the above inequalities using a fading memory estimate. And I want to say that with a fading memory estimate, the external, let's say the external signal, the past values of the external signal have less effect on the state than the current values of the external signals. Okay, and the fading memory estimates are very important whenever ones want to use a small gain theory, which is actually the core of our approach. Okay, so we define now some quantities, which involves now this exponential term here. Okay, and we write this and we enforce these inequalities. Yeah, we reinforce these inequalities. And next, we use the triggering condition because we want to guarantee this inequality. Again, we want to keep this error small enough. We use kind of fading memory estimates as well on some other computations to obtain this inequality. And we enforce this inequality that we plug here. Let me show you rapidly here. So the point is that at the end, we can see clearly in the interconnections between the PDE, the norm of the PDE, the parabolic PDE, and the hyperbolic PDE. So it is here that small gain arguments come into play. They allow us to conclude, to obtain an estimate in terms of the initial conditions of the system, with a term here, which is well-defined and positive, right? Provided that the small gain condition holds. And this is indeed true because we started with this condition in the theorem, and which implies this condition with mu and epsilon small enough that do exist because of continuity arguments. So at the end, we obtain the global exponential stability of the target system, and we use the bounded invertibility of the backstepping transformation. And finally, I want to show you some numerical examples. We consider first a reaction diffusion PDE without delay, and these initial conditions, and with lambda, the reaction parameter large enough. And we close the loop using the continuous time controller, and we compare it with the event triggered one. So here on the right, we have in red, the plot in red, we have the continuous time controller, and in black we have the event triggered one, which is we can see that it is updated aperiodically according to the event triggering condition. And here we have the numerical solutions of the PDE, of the reaction diffusion PDE, using the continuous time controller, and here using the event trigger control. Okay. And now, if we consider time delay 0.5 units of time, again with the same initial conditions and the same reaction parameter, we close the loop again, and we can see first that, well, the control action, the control effort is higher than in the delay-free case, and also we can see the event triggered control, which is updated aperiodically. Here we have the numerical solution for both the parabolic part and the hyperbolic part under the continuous time controller, right? And here we have the same numerical solutions using the event trigger controller. So notice here that we have piecewise constant signals. We can see the discontinuities propagating through spatial domain. The signals reaches the boundary condition of the heat, and then we can guarantee that even though we are dealing with errors, we obtain the global exponential stability of the closed loop system. We talked a lot about the target system, so we wanted to see what happens with the numerical solution of the target system. So in particular here, the perturbed target system, and here we have the deviation fluctuation, which is reset to 0 at each triggering times, and then the piecewise continuous signal propagates and reaches the parabolic part of the target system. Okay, let me share some short-term perspectives. So of course, the next step is to study event-triggered output feedback for reaction diffusion PDEs with input delays. This calls for an observer-based design. So surely the triggering condition will depend only on the output and on the estimated states. But we have to overcome a limitation that we encounter in, I think, every observer-based design for event trigger control, even for finite-dimensional systems, and it's the fact that the output is measured. We can take measures of the output continuously. So we should be taking the output sporadically, for example, periodically. So this calls for sample data observers that can be combined with an event trigger control scheme. Another perspective is, of course, I forgot to say, this is very, very challenging. We try to sample the output as well. This is something we've been working on. And okay, so the another perspective is event trigger gain scheduling plus together with event trigger boundary control. In the case when we consider time and space varying reaction coefficients, and also if we consider delays. So we have produced a result on event trigger gain scheduling, but the result for event trigger control is still missing. Okay, in particular, if we consider delays. Okay, so it would be interesting to apply the results to epidemics, as I motivated at the beginning of the talk. And here I would like to point out a couple of open problems. One of them is, can we derive a Lyapunov-based event triggering condition in the case we consider G-like actuation and disturbance at the boundary? As I said, as far as I know, perhaps I should be asking Andre if the scenario has changed, but as far as I know, there is still the lack of an ISS coercive Lyapunov function. And the other, another open problem is the design of robust event trigger controllers in the presence of external disturbances and measurement noise. This is critical because external disturbances, for example, can induce the Zeno phenomenon. Okay, with this, I finish my presentation. Special thanks to Yasun Karafilis, whose previous works on ISS for PDEs and sample data control have been very helpful, and also for his mentorship and fruitful discussions we have had so far. Thank you, and I'll be happy to take questions.